What is up, you guys? So in this one, we're going to introduce you to SymPy's linear algebra features. We're going to see a lot of cool stuff that you're capable of doing using SymPy. It makes linear algebra really easy. You can perform a whole lot of tasks from eigenvalue decomposition to LU decomposition, reduce row echelon forms. You can also multiply, add, subtract matrices. You could also compute more sophisticated stuff such as the column space, the row space, and the Eigen space of any matrix. So without further ado, let's get started. So the first thing you'd want to do is open your terminal. Say I go to my desktop, I create a folder called Matrices on SymPy. I cd into that, and I'll open my Jupyter notebook. Okay, I'll create a new Python 3 notebook, and given that I have SymPy installed, if you don't know how to install SymPy using your terminal, I'm going to leave a link down in the description section below on my previous video detailing how to get the job done. So first we're going to import SymPy. So from SymPy import asterisk as such. And to create a basic matrix, let's say I want to create the following matrix on SymPy. All I have to do is call matrix, then pass the rows of that matrix. So let's say my matrix is composed of the first row being, let's say, 1 0, the second row 6 8, and the third row -1 7. Run, and there you see you have a very nice formatted matrix. You can get its LaTeX code or the MathML code as such. So this is the LaTeX code, and here's the MathML code for that matrix. Okay, so let's say I store that matrix in A, and let's say I want to display A again. There you go. Let's say I create a vector X, call it matrix containing 1 3. Then X looks like this. Okay, and actually let's add one more element, let's say 5, and there you go. Let's say I want to find the product X times A. There you go. So you simply multiply them as easy as using the asterisk sign. So speaking of multiplication, you can perform any type of basic operation. Let's say I've got the A matrix that is this, and let's say I define a B matrix that is of the same dimensions. Let's say 1 3, 4 0, and 0 1. So this is my A and this is my B. You can add those two matrices as such, A plus B. You can subtract A minus B. Can we multiply? Let's check. No, we cannot, because matrix size mismatch. You can't multiply a 3 by 2 matrix by another 3 by 2 matrix. So what you're going to do here is, let's say you multiply by the transpose of B. That's doable because B transpose is of size 2 by 3, and hence you can post multiply it by A. You get this. You can also scale a matrix. So you've got A, you can multiply 2 times A. It multiplies each and every element by 2. Now let's define a square matrix A that is 1 2 3, 3 4 5, and 5 6 7 8. This is going to give me an error because I didn't wrap all the vectors in one nice bracket as such. So this is my A matrix. There you go. You can find the square of the matrix, which is defined not as the entry-wise squaring operation, no, but it is simply A times A. You can also compute the inverse of a matrix using, so in Python, squaring or exponentiation is performed using double asterisk. There you go. So this is 2 cubed. If you want to find the inverse of 2, it's 2 to the power minus 1, right? So you'd use that to find the inverse of A. And why can I not find the inverse of A? It's because its determinant is 0. So to check, you can run a.det And there you go, its determinant is 0, so it is not invertible. Going back to A, let's redefine it. So this is my A. I'll go down here. I'll just change this value to 0. I'll check if its determinant is non-zero. It's 9, so thus it is invertible. And now I can compute the inverse as such. To make sure this is indeed the inverse, go ahead and store it in a variable called inv_a. Find the inverse. Now perform the following multiplication, inv_a times a. You get the identity. So it is the left inverse. Now is it the right inverse? Yes, it is. So there you go. You can go ahead and also do the following. So a to the power minus 2, just the following matrix. What is that? It's the inverse of a multiplied by itself. So given a matrix A, you can also go ahead and find its transpose using a dot t as such. And there you go. This is the transpose of A. Let's say you're interested in accessing some rows of that matrix. Well, it's really easy on SymPy. You can go ahead and type in a dot, so my A looks like this. So you can go ahead and type a dot row and pass the index of the row you're interested in. Let's say you want the first row, so element 0. We start counting from 0. There you go. This is the first row. Say you want the second row. This is the second row. Let's say you want the third row. Here's the third row. Can you access the fourth row? No, it gives you an error. Tells you index out of range. You can go ahead and access the last row using -1, as is the case in NumPy. And you can do the same thing for the columns, a.col column 0. This is the first column, second column, and last but not least, the third column. You can obtain it by 2 as such, or via -1. That is the last column, right? Okay, now that we know how to access rows and columns, well, the next natural question is, can we delete columns or insert columns or rows? Well, yes, it's really easy on SymPy. All you have to do, let's say this is your matrix A, and be careful. The following operations are in place. What does that mean? It means that they take effect once you call those operations. So let's say you want to delete the first row. All you have to do is call it as such. And there you go. Now A is my previous A with the first row being eliminated. Doing this one more time, you get 6, 7, and 8. Okay? Now let me redefine my A. Going back up here, I'll redefine my A. So this is my A. Now let's say I want to delete the last column. Well, a dot col for column underscore delete the last one, -1. And there you go. It's really simple. Okay, now that we could delete rows and columns, we can also apply the inverse operation, that is insertion. Could we insert rows and columns? Well, yes, very easy. And unlike deleting, inserting rows and columns is not in place. That is, when I go ahead and do this, let's say a dot row insert. So don't forget, this is my A right here. Say I want to insert a row down here. First of all, the row should be of size 1/2, right? So let's say I insert the row 1, 3. And I have to tell it where, right? So where? I want to insert it in the last index, so 3. Don't forget to type in matrix, so that this guy is a matrix to be inserted. Actually, it's a vector. It's a specific type of a matrix. And I want to insert it in the third entry. So 0, 1, 2, then in the third one, in the last one. And there you go. But if I go ahead and call A, it didn't take effect. So the proper way to do it is to say A equals to what I'm doing, right? And that's how you will get the row inserted, okay? Let's say I go ahead and insert another row, let's say 0, 0, in the second position. Well, there you go. Second means 3, so 0, 1, 2. Okay, like rows, you can insert columns. So A is equal to A dot call underscore insert. Tell it where you want to insert it. So let's say in the middle. So 1. And now pass it the column you want to insert. So let's say 1, 2, 3, 4, 5. Okay? Run, check, and there you have it. Now, as is the case in MATLAB, Python, Wolfram, and all these cool softwares, SymPy also offers the capability of defining specific type of matrices, such as the identity matrix, as simple as I. So you type in I. Let's say you want your identity matrix of size 3. And there you go. This is your identity matrix of size 3. You could also define an identity matrix of rectangular dimensions, 3, 4. So 3 by 4 identity matrix in the first 3 by 3 submatrix and zeros elsewhere. Okay? You can also define the zero matrix, so O is equal to zeros, and pass it the dimension. So let's say I want a zeros matrix of size 4 by 4. Well, there you go. 4 by 4. And in case you pass it one number, just, chooses a square matrix. You can also have a rectangular zeros matrix as such, 4 by 6. There you go. You can also create a ones matrix. Let's say A is ones, 3. If you pass it one parameter as such, it chooses a square matrix of size 3 by 3. And if you pass it two different numbers, then there you go. A matrix of all ones of size 3 by 5. Now let's say you're in a situation where you have a matrix, but you don't know the dimension of the matrix. Well, you can get that using a.shape as such. There you go. Matrix is of size 3 by 5. You access the first entry as such and the second as such. You can also define your own diagonal matrix without having to, pass as such. Say you want a 3 by 3 diagonal matrix with elements containing, I don't know, say 1, 0, 0, then 0, 5, 0, then 0, 0, 9, right? You print your A, you've got your diagonal matrix. Well, this is, has a lot of redundancy. You've got zeros, and it's a specific type of a matrix, a diagonal matrix. You could make use of SymPy's diag function. So diag as such, go ahead and pass 1, 5, and 9. There you go. As simple as that. Now this is very useful when you're working with block matrices. Let me show you what I mean. So let's say you want the following matrix. So you've got matrix. Let's say you've got the following matrix. Let's say 4, 0, 0, 0. I'm just going to type in a matrix over here. Nothing fancy. So the first row is 4, 0, 0, 0. The second row is 0, 2, 2, 0. The third one is also 0, 2, 2, 0. The fourth row is 0, 0, 0, 6. The fifth row is 0, 0, 0, 8. And the last row is 0, 0, 0, 9 as such. Let's see how the matrix looks like. As you can see, it resembles a block form. So you've got 4 over, it's a block diagonal matrix, to be more specific. It has the first submatrix 4, then the second submatrix 2, 2, 2, 2, then the last submatrix 6, 8, 9. Well, you can also profit from your diag function to create this matrix. So notice that 4 is on the first subdiagonal part. Then you've got a matrix containing 2, 2, or we can, we can make use of ones, 2, 2, then multiply it by 2, right? Because that, if I copy paste it right here, it's this matrix right here, right? So I'm scaling my ones matrix to get this 2, 2, 2, 2, right? Okay, and in the last entry I've got 6, 8, 9. This is my B. Let's go ahead and check if it is indeed A. And there you go. Everything is 0 except 4, then the 2, 2, 2, 2, then the 6, 8, 9. So diagonal is not only useful in case of a diagonal matrix, but also could be generalized to block diagonal ones. Okay. Okay, now let's say I've got a matrix, right? Matrix, let's say 1, 2, 0, 0, 3, 4, 5, and 5, 6, 8, 7, 8. Okay, this is my A. Let's say I've got a B that is 1, 2, 3. Okay, so this is my A, this is my B. Oh, and by the way, just before I continue, in case you wrap this as such, B is a row vector, but in case you leave it as such, it's a column vector. Okay, it's very handy because you know you can obtain a column by wrapping as such and then apply a dot T. You can get the job done, but this is simpler in case of vectors. Okay, let us work with the following system: ax equal b. I have my a, I have my b, and I want to compute my x. Okay, first let's check if this system is solvable. So a dot det, it's 9, so a is invertible, and so my x is a inverse times b. I take a look at my x, it looks like this. Good. Well, what we just did is solve the system of linear equations using matrix inversion. Well, you can also solve it using reduced row echelon form. From what you know in linear algebra, and if you have no idea of what our reduced row echelon form is, it's okay, you can skip this section of the lecture. And if you're curious to know what reduced row echelon form is, I'm going to leave a link to my linear algebra lecture explaining that, and what it's used for is also solving systems of the following form: ax equal b. And this is achieved by creating a bigger augmented matrix, usually referred to as augmented matrix. And what we're going to do is we're going to insert on top of A, we're going to insert in the last entry, we're going to insert B. Take a look at A, it is as such. So we've got A in the first 3 columns and B in the last column. Now that we have our augmented matrix, all we have to do is run A dot rref as such. Really easy. So taking a look at what we have, so we've got a 1 element list, so accessing it by 0. There you go. This is your system in reduced row echelon form. And so what's useful about this is that the last column is actually your x, your solution. Minus 5 over 9, 7 over 9, 1 over 9. Minus 5 over 9, 7 over 9, 1 over 9. Okay? Now let's say I accidentally, let's say I created a matrix as such. 1, 2, 3, 3, 4, 5, and 5, 6, 7. What is the determinant of A? It's 0. And so if I want to go ahead and solve the following system, ax equal b, well, I cannot, because simply the inverse of A does not exist. And there you go. The determinant is 0, matrix is not invertible. And so let's say I want to take a look at how the reduced row echelon form looks like. So you go back up here, you insert, as you did, you insert B in the last column, and then you run an rref, and you take a look at the matrix. And as you can see, the last row is all zeros. Rewriting the system in expanded form, it means that x1 minus x3 is 0, x2 plus 2x3 is half. And what that means is that x1 is x3 and x2 is half minus 2x3. So the system admits an infinite number of solutions. So your solutions take the following form. It is the set for all x3 in R. It is the triplet x3, half minus 2x3, and again x3. Okay? This is the solution set of the system. Where is it? ax equal b. Okay? Other than reduced row echelon forms, you can go ahead and compute the so-called null space of a certain matrix. And what is the null space? So it's all vectors in Rn that null A out by post-multiplying from the right. So if I perform A times any vector from this set, it should return 0. And so let's say I've got a matrix. Let's go back up here, find us a matrix. This is a matrix A. There you go. Well, let's say we want the null space of that matrix. Well, it's super easy on SymPy. All you have to do is call a dot null space. As simple as that. And there you go. There's the null space. We can extract the null space as such. So this is v1. It is the first element. There you go. So this vector is supposed to null my a out. Let's check. A times v1. It's all zeros. So it is indeed a vector that lies in the null space of A. Well, let's get another example where A has no null space. Well, the reason that A over here had a null space is because its determinant is 0, so it has a null space. Let's find a matrix that does not have a determinant equal to 0. I'll get my A from here. I'll set this guy to 0, and I'll check the determinant. It is 6, and so it is not 0, and hence it is invertible. And so it does not admit any null space. Well, let's check that out on SymPy. A dot null space, it's empty. So there is no vector that could null your A out. Now, like the null space, we have something called the column space of A. In other words, it's the image of the matrix transformation that we have. So it's all possible outputs of that matrix, okay? So you get all possible x's and produce the following product, A times x. In linear algebra, the column space of A is also known as the span of the column vectors of A. That is, it is the set of all possible linear combinations of A, because I can go ahead and write this set as follows. Because suppose my A contains columns denoted by A1, A2 up till AN, and similarly, vector X contains scalars denoted by x1, x2 up till xn. Well, see all those linear combinations? They're the ones that are producing all the possible y vectors that lie in the column of A. So on SymPy, you can get all, let's say you've got a matrix A, you can get its column space as such. There you go, 1, 3, 5, 2, 4, 6, 0, 5, 7. Now, that's not really useful here because it's just returned my columns. Well, we can't say it's not useful. Why? Because this matrix is full rank. Go ahead and check the determinant. It's not 0. And let's say I have the following matrix. Well, I'm going to create a matrix that is rank deficient. That is, let's say, it looks like this. Let's say it looks like this. So this is my A, and I don't know if you've noticed, but the first column plus the second column is actually the third column. So there's a linear, so the third column is a result of the first and second column, and hence the rank of this matrix, so you can go ahead and compute the rank as well, is 2, not 3. That's because the determinant is 0. Well, it is at most 2. Because the determinant is 0. The determinant tells you, your matrix is not full rank, but it doesn't tell you how many ranks it needs to become full rank, if that makes sense. You could capture this by the rank. You could also capture it by the column space. So how many columns do I need to generate my matrix? I need 2 columns only. And I have a problem here because this does not contain an underscore as such. And there you go. Your 2 columns are 1, 2, 3 and 1, 1, 1. We don't need the last column because it's just a linear combination of the previous 2. This also works for scaling as well. So let's say I have a 2, 2, 2 as such. Okay. You see that the third column is simply 2 times the second column, right? The rank is still 2, determinant is still 0. And your column space is still the same. Now we can't talk about linear algebra without at least speaking on eigenvalues and eigenvectors. Well, let's say you've got the following matrix, M, that is a matrix containing the following rows, so 3 minus 2, 4 minus 2, 5, 3 minus 3, minus 2, 5 minus 2, 2 minus 2, and last but not least, 5 minus 2 minus 3 and 3. So my M looks like this, and let's say I'm in a situation where I'm interested in the eigenvalues of that matrix. You can get the eigenvalues as simple as M dot Eigenvalues as such. And as you can see, SymPy returns a dictionary to make sure. Save E, type in the type of E. Tells you it's a dictionary. Now, to extract the elements of E, all you have to do now you use Python for Eig in E, print E as such, Eig as such. So 3 minus 2 and 5 are the eigenvalues. But those are the keys. The eigenvalues are actually the keys of what you have. But what is this number, the value of each key? It is the algebraic multiplicity of that eigenvalue. So you can go ahead and say, now let me insert this as a string. Go ahead and say is an eigenvalue with algebraic multiplicity of, and you can go ahead and do E of Eig as such. There you go. 3 is an eigenvalue with algebraic multiplicity of 1, minus 2 as well, and 5 is an eigenvalue with algebraic multiplicity of 2. Now that we know how to get the eigenvalues, let's say you want to get the eigenvectors. Well, you go m dot eigenvects as such. And there you go. It's a list where each entry consists of the eigenvalue, its algebraic multiplicity, and its corresponding eigenvector. Now, as you can see, since minus 2 is an eigenvalue of algebraic multiplicity 1, then it has only one eigenvector attached to it. 3 as well. However, 5 is of algebraic multiplicity 2, and so it has 2 eigenvectors attached to it. Do not forget the formula of eigenvalue eigenvectors, that is lambda I vi are eigenvalues eigenvectors if a vi is lambda I vi. So let's go ahead and extract my vi's, right, in a suitable way. So my v1 is, if I go up here, save all this guy in a v, it is v0. If I go ahead and do this, then what I have is eigenvalue, multiplicity, and eigenvector. I need the last element, so 2. And there you go. It's the first element. So this is v1. Likewise, v2. There you go. This is v2. And v3 has 2 eigenvectors. So what I'm going to do is this. v3, it is the second one, the first element in the second one, and v4 is the second element in the third one. So v3 is this, and v4 is this. Now that I have my, actually let's go ahead and extract the eigenvalues as such. So lambda 1 is, so I'll copy paste all this right here. I'll replace the v's by lambdas. Lambda 1, lambda 2, lambda 3, lambda 4. And right here, what I'm going to extract is the first element of each. So go ahead and type lambda 1, it's minus 2, lambda 2, 3, lambda 3, 5, and lambda 4 is also 5. Now to verify that they are indeed eigenvalues, eigenvectors using this formula, well, go ahead and multiply m by v1. You get this. Now, is it equal to lambda 1 v1? Well, yes, it is. So v1 lambda 1 is an eigenpair. Let's do the same thing. v2, you get this. Lambda 2 times v2 is the same. v3, lambda 3, v3. There you go. Now that we introduced eigenvalues, eigenvectors, we can also perform, thanks to eigenvalues and eigenvectors of SymPy, we can also perform diagonalization using SymPy. And what diagonalization is the following. It's decomposing m into PD, p minus 1, where d is diagonal, containing eigenvalues in its diagonal entries, and p is a matrix containing the eigenvectors. So you can obtain P and D simply using diagonalize as such. So it returns P and D. So P is this matrix, and D is the diagonal matrix containing, so P contains the eigenvectors stacked as such. So go up, so checking V1 is in the first column along with lambda 1 and the first entry of the diagonal matrix. Go ahead and check V2, all ones, second column, and associated to it there's lambda 2 right here, lambda 2. Also you've got V3 1110 with lambda 3 5, and lambda 4 is lambda 3 because the multiplicity of the algebraic multiplicity of eigenvalue 5 is 2, so you've got 5 repeated twice, and V4 is in the last column, right? You can also verify that P times T times P inverse is indeed the matrix M as such. Now let's say you're in a situation where, okay, I know the eigenvalues, I know the eigenvectors, but I'm not interested in them. What I'm interested in is the characteristic polynomial of matrix M. Well, you can obtain it really easily on SymPy. All you have to do is, so you can go ahead and create your lambda as such. So you define a symbol using SymPy's symbols, L for lambda. So you create a symbol that is L, stands for lambda. And after that, you go ahead and call m dot char poly, short for characteristic polynomial of lambda. So now you have your P of lambda. Let's see how it looks like. It's a pure polynomial as such, so it's in expanded form. Let's try to factor it. So factor P, still in expanded form because I didn't do it properly. You have to enter P dot as underscore expression. That's from the previous lecture. There you go. L minus 5 squared, which explains why 5 is of algebraic multiplicity 2, because it's repeated twice in this factored form. 3 is an eigenvalue of multiplicity 1, and minus 2 is of algebraic multiplicity 1. Oh, and by the way, if you insist on the lambda symbol, you don't type in lambda as such, you omit the B, so you end up with a D. And there you go. It's because lambda is reserved for, I think, lambda expressions on Python. You can also perform LU decompositions of matrices. That is, you go ahead and decompose A as two matrices, L times U, where L is lower triangular and U is upper triangular. What that means is that L is a matrix with all zeros and all entries that lie above the diagonal, and upper triangular is a matrix that contains zeros in all elements that are lower than the diagonal. Well, let's say you've got the following A, 1, 2, 3, 3, 4, 0, and 0, 4, 1 as such. So this is my A. All you have to do is type in A dot LU decomposition as such. There you go. You've got the two matrices. L is in the first entry and U is in the second one. Go ahead and type L. There you go. A matrix with all zeros in the upper part, and U, a matrix with all zeros in the lower part. To verify that this is correct, go ahead and multiply L by U and take a look at A. It is indeed the same matrix. A small note on echelon forms, going back up to the echelon part of the lecture. So this is my AA. Let's say you want to ask the question, is A in echelon form? Well, you can go ahead and do this. AA dot is echelon as such. Tells you false. It is not in echelon form. However, after performing the reduced row echelon form, let's save it in B, for example, and ask the same question. Is it in echelon form? True, it is. So that's about it. That's all I have to say on linear algebra functionality on SymPy. We did a whole lot of stuff. We showed you almost all the features of SymPy's linear algebra tools, starting from how to create a matrix, to how to multiply matrices with vectors and even matrices, how to add, subtract matrices, how to perform matrix transposition, how to scale a matrix, how to perform matrix exponentiation, matrix inverse, how to compute a determinant of a matrix, how to extract certain rows and columns from the matrix, how to delete them as well, and how to insert rows and columns into matrices. We also talked about specific type of matrices that are the identity matrix, the zeros matrix, and the all ones matrix. We showed you how to extract the dimensions of any matrix in SymPy and how to create diagonal and block diagonal matrices on SymPy. Following this, we showed you how to perform reduced row echelon form operations on augmented matrices for the purpose of solving linear systems. And then we showed you how to compute the null space of a matrix and a column space of a matrix. Following this, we talked about eigenvalue and eigenvector computations on SymPy, and we showed you how to perform eigenvalue decompositions, that is diagonalization of matrices, and how to compute its characteristic polynomial. Finally, we talked about a specific type of decomposition that is called the LU decomposition, or lower upper triangular decomposition, where a matrix is decomposed into product of two matrices where one is lower triangular and the other is upper triangular. So thanks for watching. In case you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below. I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish. Thanks for watching, and I'll see you in future lectures.